As we know, in the world of refrigeration and air conditioning, the performance of the piston compressor has been much questioned lately.
However, without a doubt, this type of machine is still preferred by many technicians, due to its possible repair, the sale of new spare parts and its high reliability. For this reason, to improve the performance of piston compressors, their manufacturers have worked on perhaps the most influential factor in electricity consumption. We are referring to the control of the compressor's cooling capacity or the way to only produce the cold that needed, avoiding the on-off dimming method. Currently, capacity regulation mechanisms in reciprocating compressors are well known, using unloaders and the digital regulation method. Both methods are very similar, because they seek to eliminate the suction of coolant in the pistons that are not needed. The main difference between these two methods is that the regulation by arresters works by capacity ranges, while the digital method works almost at the same rate as the need for cooling. Next, we will explain these two methods in more detail. Piston compressor capacity control in refrigeration and air conditioning with unloaders. 1. When the operating conditions of the refrigeration or air conditioning system are not so severe, that is, when the cooling load is lower than the design load, or the outdoor environment temperature is low, then at that time it is necessary to regulate the capacity of the piston compressor. 2. By not taking a control action, the compressor is left operating at a lower evaporating temperature, which can affect the refrigerated space. 3. The evaporator temperature during part load conditions is reduced as the rate at which refrigerant vapor is drawn into the compressor exceeds the rate of vaporization in the evaporator. 4. Low temperature operation of the evaporator can cause problems such as low air humidity, frosting of the evaporator coils, and freezing of the external fluid. Most large reciprocating compressors, above 10 tons, 35 kilowatts, are equipped with cylinder unloaders. 5. The unloaders are used to match the refrigerant flow capacity of the compressor to that required by the application. 6. The regulation is achieved with the progressive deactivation or activation of the passage of refrigerant to the compression chamber of the piston compressor. 7. In response to a decreasing load, an electronic controller sends an electrical current to activate a solenoid. 8. This solenoid valve diverts the compressor discharge pressurized refrigerant vapor to the top to shut off the flow of refrigerant vapor to the cylinder suction. 9. Even though the piston continues to travel back and forth within this cylinder, it no longer performs compression as it cannot absorb refrigerant vapor. 10. In response to an increasing load, the controller sends a signal to close the solenoid valve. This closes the port, not allowing the pressurized refrigerant vapor to pass to the top. In this way, the intake of refrigerant gas is opened. 11. A controlled leak rate around the discharge valve relieves pressure, allowing the valve to open and refrigerant to once again flow into the cylinder to be compressed. Now we are going to study the management of the unloaders of a 6-piston reciprocating compressor, using the following graph. 1. A plot of compressor capacity against suction temperature, assuming a constant condensing temperature, reveals that compressor capacity increases as suction temperature increases. 2. When the temperature and suction pressure increase, the refrigerant in vapor form becomes more dense. 3. Therefore, a greater amount of refrigerant can be compressed in a given compression cycle, thus the capacity of the compressor is greater. 4. In this compressor, 4 of the 6 cylinders are fitted with unloaders and are unloaded in pairs. 5. At design conditions, the evaporator and compressor capacities are balanced at a suction temperature of 45 degrees Fahrenheit, 7.2 degrees Celsius and a capacity of 31 tons, 109 kilowatts. 6. As the cooling load decreases below this break-even point, assuming constant condensing pressure, the pumping capacity of the compressor decreases with decreasing suction temperature along the 6-cylinder curve until it reaches the break-even point. B. 7. Here, the compressor discharges the first set of 2 cylinders. When the first set of 2 cylinders is unloaded, the compressor runs with only 4 active cylinders, and compressor capacity immediately drops to 19 tons, 66.8 kilowatts, along the C4 cylinder curve. 8. As the charge continues to decrease, the capacity and suction temperature follow the 4-cylinder curve until it reaches point D. 9. Here the second set of 2 cylinders is unloaded, decreasing the compressor capacity to 9.5 tons, 33.4 kilowatts along the curve of 2 cylinders E10. As the load continues to decrease, the suction temperature reaches the set point minimum of 28 degree F minus 2.2 degree C, in this example point F. Here the cylinders are deactivated by turning off the compressor. 11. The minimum compressor capacity in this example is 7 tons, 24.6 kilowatts. This illustrates how cylinder unloading extends the part load stable range of a reciprocating compressor. Let's go with part 2 of the video, where we are going to explain the digital type capacity control in piston compressors. Unlike the unloaders, where activation and deactivation by capacity ranges were used in the digital method, it is controlled by quickly activating and deactivating, with a determined frequency, the passage and non-passage of refrigerant to the compressor suction. We are going to look at Copeland's range of digital type reciprocating compressors known as digital drives. Let's start by saying that this range of reciprocating compressors have 3 cylinders with continuous capacity modulation, without a frequency inverter. The characteristics of the digital disc compressor are 1. The 3-cylinder digital discus series compressors are an alternative to a variable frequency drive to achieve continuous capacity modulation. 2. Digital modulation is the simplest and most accurate method of controlling reciprocating compressor capacity with the least applied cost. 3. Digital technology is based on the control of a cyclical form of a special solenoid valve that is inserted in the cylinder head of the compressor. 4. The solenoid valve actuates a piston that controls the entry of gas to the suction area of the valve plate of the disc compressor. The idea is to prevent refrigerant gas from entering certain cylinders, to only compress the necessary amount of gas. 5. The compressor always runs at a constant speed, which prevents potential oil return problems and eliminates mechanical and electrical stress on the system. 6. It is a range of 6 models from 32 to 50 cubic meter per hour. 7. Continuous modulation from 10% to 100% that guarantees a perfect adaptation of the capacity and power to the cooling load. 8. Cheaper and more reliable alternative to variable frequency drives. 9. Precise control of the evaporation pressure, associated with energy savings and stable evaporation temperatures. 10. Quick and easy integration into the refrigeration equipment, similar to any other standard compressor. 11. Possibility of incorporating it into existing installations, just by replacing the cylinder head and the valve plate. 12. No vibrations or mechanical stress on the pipes or on the compressor parts. 13. Reduces starts and stops, thus extending the useful life of the contractor and compressor. 14. Large starting current peaks are avoided. 15. Some potential interference problems that may be caused by some inverter electronic modules are avoided. 16. The digital discus compressor is doubly efficient because it has a low dead volume and only the gas you need is compressed. 17. On the screen we are showing the refrigeration capacity that can be achieved with some of the models of the digital discus series.